one's ever done anything like this before.
It's the most ambitious and complex space science mission.
I believe this is going to be our finest hour.
Treating a quadruple failure is heck yeah.
More than 2 years after its successful launch, the James Webb Space Telescope has entered what can only be described as a golden age of discovery. With every new observation, it continues to push beyond the limits of what we once believed was possible to see. It is not just extending our vision into deeper space, it is pulling back the curtain on the earliest moments of the universe itself. But these discoveries haven't brought clarity alone. Instead, they've opened something far more troubling, a growing collection of contradictions that challenge the very foundation of modern cosmology. Recently, Webb once again turned its gaze toward a time period less than 500 million years after the Big Bang, an era astronomers long believed was populated only by small, immature, and rapidly forming galaxies. What it found completely defies that expectation. Instead of tiny, chaotic structures just beginning to assemble, Webb observed galaxies that appear massive, structured, and surprisingly mature, as if they had far more time to evolve than the universe had actually given them. And among these discoveries is one galaxy that stands out in a way that is difficult to ignore. A galaxy that may be one of the oldest ever observed, and yet, paradoxically, one of the most developed. What makes this discovery truly shocking is not just its age, but its scale. This galaxy already contains billions of stars, formed and organized in a way that should not have been possible so early in cosmic history. A few years ago, this object appeared in images captured by the Hubble Space Telescope as nothing more than a faint and unremarkable speck of light. At the time, it was cataloged as unusual, but not extraordinary. No one suspected what it truly was. It wasn't until the James Webb Space Telescope focused its far more powerful instruments on that same region of space that the reality became clear. That tiny point of light wasn't a distant anomaly. It was a massive, ancient galaxy hiding at the very edge of time. Now known as GZ9P3, this galaxy exists at a redshift of 9.3, meaning we are observing it as it was just around 510 million years after the Big Bang. To put that into perspective, the universe itself is about 13.8 billion years old. So this galaxy formed in less than 4% of the universe's current age. And yet, despite this incredibly early snapshot in time, GZ9P3 doesn't behave like a young galaxy at all. It appears evolved, structured, and far too massive. While astronomers have detected other galaxies from roughly 300 to 500 million years after the Big Bang, none of them come close to matching the size, brightness, and complexity of this one. This raises a question that is becoming increasingly difficult to answer. How did something this large form so quickly? For a galaxy like GZ9P3 to reach this level of development, its stars must have formed at an extraordinarily rapid rate, far faster and more efficiently than current models of galaxy formation can explain. In simple terms, the universe may have been building galaxies much faster than we ever thought possible. But the mystery doesn't end there. When scientists examine the structure of GZ9P3 more closely, they notice something even more intriguing. The galaxy contains two distinct bright regions, two dense cores of light embedded within it. This is a strong indicator of a galactic merger, a cosmic collision between two separate galaxies that combined into one larger system. If that's the case, then what we are witnessing is not just a massive galaxy forming early, but two early galaxies merging together in the infancy of the universe, accelerating their growth even further. And that has major implications. Because it suggests that galaxy mergers, events we typically associate with later cosmic evolution, may have been happening much earlier and more frequently than we assumed. But Webb's capabilities go far beyond imaging structure. It can analyze the light from distant galaxies to determine their chemical composition, effectively allowing scientists to study the elements present in stars that existed billions of years ago. When researchers examined GZ9P3's stellar population, they found something even more surprising. They detected elements like carbon, silicon, and iron within its stars. Iron, in particular, is significant. It is one of the heaviest elements produced by stars, formed in the cores of massive stars and dispersed into space through supernova explosions. Its presence means that multiple generations of stars must have already formed, evolved, and died within this galaxy, all within the first 500 million years of the universe. That timeline is incredibly tight. It suggests that star formation, stellar evolution, and chemical enrichment were happening at a pace far beyond what current theories predict. Even more unexpectedly, the galaxy appears to host a substantial population of older stars, not just newly formed ones. This indicates that star formation may have begun even earlier than we currently believe, possibly far earlier. And if that's true, then our entire timeline of cosmic evolution may need to be reconsidered. These findings point toward a deeper issue, one that extends beyond a single galaxy. Because GZ9P3 is not an isolated case. It is part of a growing list of observations that don't quite fit within our existing framework. And this brings us to a much larger problem in modern astrophysics, something scientists often refer to as the crisis in cosmology. At its core, this crisis stems from the fact that different methods of measuring the universe are producing conflicting results. One of the most well-known examples of this is the Hubble tension. The universe is expanding, that much we know. Galaxies are moving away from each other, and the rate at which this happens is described by a value known as the Hubble constant. But here's where things get complicated. When scientists calculate this expansion rate using the cosmic microwave background, the faint afterglow of the Big Bang from when the universe was about 380,000 years old, they get one value. But when they measure it using distant supernovae, objects whose brightness can be used as cosmic distance markers, they get a different value. These two measurements should agree, but they don't. And the gap between them has persisted for years. Now, with the James Webb Space Telescope providing even more precise observations, this discrepancy has only become more pronounced. Webb has effectively confirmed that the Hubble tension is real, and not the result of simple measurement errors, which leaves scientists with a troubling possibility. There may be something fundamentally missing from our understanding of how the universe works. But that's not the only inconsistency. Another emerging issue is known as the S8 tension, a problem related to how matter is distributed throughout the universe. In simple terms, scientists are trying to understand how clumpy the universe is, how matter gathers and clusters on large scales. Different methods of measuring this clustering once again produce conflicting results. Observations of nearby galaxies suggest that matter is less clustered than expected, but models based on early universe data suggest it should be more tightly grouped. To address this, researchers turn to one of the most ambitious computational projects ever undertaken in cosmology, a massive simulation known as FLAMINGO. This project aimed to recreate the evolution of the universe using one of the most powerful supercomputers available, the COSMA 8 system in the UK. The scale of this effort is almost difficult to comprehend. It required more than 50 million hours of computing time, spread across tens of thousands of processors. And unlike earlier simulations, FLAMINGO didn't just focus on dark matter. It also incorporated baryonic matter, the normal matter that makes up stars, gas, and galaxies, along with complex processes like supernova explosions and black hole-driven winds. These processes, while often overlooked, can significantly influence how matter behaves and distributes itself across the cosmos. The goal was simple: resolve the discrepancies, bring theory and observation into alignment. But that's not what happened. Despite its sophistication, the FLAMINGO simulation failed to fully explain the observed distribution of matter. In fact, it couldn't resolve the S8 tension at all, and in some cases, it highlighted the inconsistencies even further, which raises a difficult question. What if the problem isn't the data? What if the problem is the model itself? Because now, we have observations from Webb, measurements of cosmic expansion, and large-scale simulations, all pointing toward the same conclusion: something isn't adding up. The standard model of cosmology, the framework we've relied on for decades, may not be entirely wrong, but it may be incomplete or missing something critical. And that opens the door to new possibilities. Some emerging theories are beginning to explore ideas that were once considered too radical, including modifications to gravity, new forms of energy, or even rethinking the role of dark matter entirely. None of these ideas have been confirmed, but the fact that they are being seriously considered tells you just how deep this mystery goes. So now, we find ourselves at a crossroads. Armed with the most powerful telescope ever built, the most detailed simulations ever created, and yet more uncertainty than ever before. Because the deeper we look into the universe, the less certain we become about how it actually works. So the question is no longer just what we're seeing. The real question is, have we misunderstood the universe from the very beginning? And if we have, what else is waiting to be discovered?